Hello everyone. In this video we are going to discuss a problem on dependence of voltage on reactive power. And the problem is as follow. Here we are considering a single phase 220 kV line of length 200 kilometer. You can see here the length is 200 kilometer with a resistance per kilometer is 0.031 ohm and the reactance per kilometer is 0.32 ohm. You can see here the resistance and reactance is per kilometer they have mentioned, and we need to compute the sending end voltage with accurate and approximate formula. If the load is 500 megawatt at a power factor of 0.85, now we are going to find the sending end voltage. Okay, let us start the solution. Before starting the problem, we need to define the base values. Okay, let us choose a base of 100 MVA 220 kV. This is our base value. Okay, and for the given problem they had given P as 500 megawatt and power factor, which means cos phi as 0.85. Okay, since these two are mentioned, now we are going to convert the given power into per unit value. Now P is equal to 500 divided by the base value, which means 100 gives us the per unit. 500 by 100 is 5 per unit. We are converting the given values into per unit values so that computations become easier. Now since cos phi is 0.85, the value of phi will be equal to cos inverse of 0.85, which is 31.79 degree. Phi is 31.79 degree. Since we got the value of phi, we can calculate sin phi value. Sin phi is nothing but sin of 31.79. Sin of 31.79 will be 0.5268. This will be the value of sin phi. Now we got the base value and the per unit value of real power, and we also calculated the value of phi and sin phi. Moving on to the reactive power calculation. To find out reactive power, we know Q is equal to VI sin phi. In this we know the value of V, we know the value of sin phi, but we don't know the value of I. To calculate I, since in the given question they have only mentioned the value of V, not mentioned the value of I, so we need to calculate the value of I. We know one more formula, real power P is equal to VI cos phi. In this formula we know the value of P, we know the value of V, and we know the value of cos phi. So the only unknown parameter is I. We can calculate I with this. I is equal to P divided by V cos phi. Substituting the value of P as 500 mega divided by 220 kilo into cos phi is 0.85 leads to the value of I as 2.67 milliamps. Substituting the value of I in this, Q is equal to V, which means 220 kilo, into I, which means 2.67 milli into sin phi is as we calculated previously, sin phi is 0.5268, 0.5268. Now q is equal to 309.88 MVAR. This is the actual value. If you convert it into per unit, 309.88 divided by 100 leads to 3.09 per unit. Since the base value is 100 megawatt, we are going to divide it by 100. 309.88 divided by 100 leads to 3.09 per unit. Now we got the per unit value of P, per unit value of Q. Let us find the base impedance value. The base impedance is equal to kV square divided by MVA, which is equal to kV square is 220 square divided by base MVA is 100, which leads to 484 ohm. This is our base impedance value. Since we got the base impedance value, now we are going to find the per unit value of resistance and reactance. Since we know the resistance per kilometer value, we will find the resistance and reactance for the whole 200 kilometer length. For a length of 200 kilometer, for length of 200 kilometer, R is equal to 0.031 into 200, which is equal to 6.2 ohm, which is equal to 0.01281 per unit, which means R per kilometer is 0.031 multiplied to the whole length 200 kilometer leads to 6.21 ohm. This is our actual resistance for 200 kilometer. Now we are going to divide 6.2 by the base impedance 484. 6.2 divided by 484 leads to the per unit value. Okay. Similarly, for reactance, 0 x is equal to 0.32 into 200, which is equal to 64 ohm. 64 divided by 484 leads to 0.1322 per unit. 0.01. You can see here R is 0.031 per kilometer. We are multiplying for 200 kilometer length. Similarly, reactance is 0.32 multiplied for 200 leads to 64. 64 divided by base impedance 484 leads to 0.1322. Okay, and the voltage V is 220 kilovolt in the given, and to convert it into per unit value, we have taken the base value as 220 kilovolt and the given is also 220. So 220 divided by 220 is 1 per unit. We got the base value of all the parameters. Now we need to calculate the sending end voltage. To calculate sending end voltage with accurate formula, first thing is they have asked for calculate the sending end voltage with accurate and approximate. Now we are going to find with respect to accurate formula. First one is accurate formula. Accurate formula is E square is equal to V plus RP divided by V plus XQ divided by V whole square plus XP divided by V minus RQ divided by V whole square. V is 1 per unit, R is 0.0128 per unit, P is as we calculated, P is 5 per unit, and X is 0.1322 per unit, and Q is as calculated, Q is 3.09 per unit. Substituting all the values, E square is equal to V is 1 plus R is 0.0128, 1 into P is 5 divided by V is 1 plus X is 0.1322 into Q is 3.09 divided by 1 whole square plus again X value is 0.1322 into P is 5 divided by 1 minus R is 0.01281 into Q is 3.09 divided by 1 whole square. On solving this, we'll be getting E square is equal to 2.54, which means E is equal to 1.59 per unit. Okay, with respect to accurate formula including resistance, okay, considering resistance with accurate formula, we got the value of E as 1.59 per unit. What if we neglect the resistance with accurate formula? Okay, let us neglect the value of R, marking R as 0 in the accurate formula. This tends to 0. We'll be left with if we neglect resistance, E square will be equal to V plus XQ divided by V whole square plus X into P divided by V whole square. Same accurate formula as we solved earlier. Same formula neglecting resistance. And substituting the values, V is 1 plus X is 0.1322 into Q is 3.09 divided by 1 whole square plus X is again 0.1322 into 5 divided by 1 whole square leads to 2.41. E square is equal to 2.41, which means E is equal to 1.55. You can see, considering the resistance value, the value of E is 1.59 per unit. Neglecting resistance value, E is equal to 1.55 per unit. Okay, the percentage error is equal to 1.59 minus 1.55 divided by 1.59 into 100 will be 2.5%. Okay, including resistance and neglecting resistance, only the difference is 2.5%. Okay, This is the value of voltage for accurate formula 1.55 per unit, neglecting resistance, including resistance 1.59 per unit. If we go for approximate formula, then again voltage E is equal to X into Q divided by V plus V is the approximate formula. Okay, E is equal to X value is 0.1322 into Q is 3.09 divided by 1 plus 1. On solving this, we will be getting E is equal to 1.407 per unit. This is for approximate formula, and the percentage error is equal to 1.59 minus 1.407 divided by 1.59 into 100. It is 11.5%. Percentage error is 11.5% for approximate formula. Percentage error is 2.5% for accurate formula, neglecting the resistance. And the sending end voltage is actual sending end voltage is 1.59 per unit for approximate accurate formula, including resistance. Okay, if we go further, okay, this solves the problem. If you move further to find what is the actual sending in voltage, V is equal to 1.59 per unit, which means 220 K V into 1.59 leads to, okay, let me calculate it. Okay, 220 into 1.59 is linear 349.8 kV will be our sending end voltage, which means we need to send more voltage. This is just because of the reactive power injected. As we see here, the reactive power necessary was increased by 3.09 per unit. This was the reactive power required. Just because of the reactive power injection, the voltage is varied. Actual voltage was just 220, and now we need to go for 350 kilovolt nearly. Okay, this is what happens when we inject reactive power into the system. Okay, thank you. If any doubts, please do put a comment on my chat box. Thank you.